Thank you. And thank you to the organizers for inviting me and having a conference in such beautiful weather, and I'm not joking. So I will speak today about a joint work with Benji Weiss. And it is a work about complex functions, and it has some dynamics involved, but somehow the point of view is different from what we've seen so far. So I'm going to look at the space of entire functions, which I will denote by curly E. But I'm going to look at it as a Polish space. So when I say Polish space, I mean locally compact, metrizable space. And I will take a look at the following action of translation. So T takes a complex number and returns a map from entire functions to entire functions. And it is defined by, so T W of you eat an entire function. And I need to tell you what is the new entire function that you get. So this is just going to be a translation of this function. And I will call this a translation. Now, Mackey asked back in the day, many, many years ago, does there exist a probability measure on the space of entire functions? I will lift it up in a sec. Which is translation invariant. Okay. So a little bit of history about this. The history starts quite a long time ago. The first result was a result by Weiss, the son Benji Weiss, in '96, where he said that the answer is yes. And more than that, he said that there's an abundance, so that there are many, many such systems with different interesting dynamics. And then in his paper, he asked about his growth. So this brings us to the second result, which was done by Buchowski, myself, Sasha Loganov, and Misha Sodin. That was done in 2018. I think it was published in 2019. And we showed two things. We actually showed more, but I'll just state these two things. We showed that the log of the maximum modulus of these functions on those disks, it has to grow like e to the log 2 minus epsilon of r. And we also found an example where it can grow up to log 2 plus epsilon of r. But that was a very particular example, unlike what Benji showed, because he showed the many and we showed one. Then the following year, I showed that you can do many, but you have to pay some price. So now the growth, instead of being log 2 to the plus epsilon, the growth is going to be e to the log 3 plus epsilon r. And then I kind of related to what Oleg said in the morning. We analysts, we hate those epsilons. So in the following year, so again, I think it got published in 2022, maybe it's 2021. I also showed that the epsilon in the lower bound is redundant. So the correct statement should be use red. This is not needed. It's just 2. Okay, great. Now let me continue a little bit more with the history. But it's now a bit of a different history. It's related, but also a bit different. So Mackey showed same Mackey who asked the question, in 1929, he showed, he constructed an entire function with a dense orbit. And then not too long ago, Siboni and Dean, not sure about the spelling of their name. Age, right? Age, and then that's what I thought, but and Siboni. I thought it was HN. Okay. So that was very recent. I think it was a paper from 2022. They had 2 questions. So the first question was, can you somehow make these results together? So can you create an entire probability measure, which is both translation invariant and almost surely functions in the support, so almost surely has a dense orbit. So that was the first question in the paper. And the second question in the paper was, what can we say about high dimensions? And I'm here to say yes, and now we can go. My talk is, no, I'm joking. In our paper, we answered both questions positively. And I would like to tell you a little bit about why this initial question was not trivial and how we did it, essentially. Okay, so I'll start with Weiss's original construction. This relates us a little bit to yesterday's morning talk. So in yesterday's morning talk, the solenoids were mentioned. And so essentially, Weiss's idea was the following. We're going to take, yes. So they wanted a probability measure, which is both translation invariant, but that the functions in the support have a dense orbit. So if you can approximate any functions with translations of this function.
What were they looking at? Why did they ask this question?
Oh no, it was just a paper with a list of questions. So it wasn't, I don't remember the name of the paper, but it's called something like a collection of problems that are still open in analysis or something like that. A good place for analysts to go hunt for questions.
So the length is infinite, right?
No, it's but yes, they do have a lot of questions. So what was Weiss's idea? He said, okay, let's look at what's called the name. It's the name of 2 people. I don't remember the first name. Boголюбов is the second name. You can define a sequence of measures by averaging along orbits of a specific function. So let me, just for the sake of it, write it here. We can define a sequence of measures. So you start with a sequence of squares, and these squares somehow saturate your entire plane. And then you define a sequence of measures, and those measures will be defined in the following way. So when I write M, I mean Lebesgue. you look at, you normalize your measure, and then what you do is you check which iterates of your functions land inside A. And it's not hard to see that this is a probability measure. And if you're particularly lucky, then maybe this will converge weakly, and maybe the support of mu will not be just constants, say an infinity. But this requires a very particular function. Okay, so if you try to run this process, for example, with polynomials, you'll get that they're supported on infinity. The measure will be supported on infinity. And so somehow you need some kind of a repetitive pattern of your function. So if you could have a periodic function, that would be perfect. But we don't have periodic entire functions. So that wouldn't work. So instead, what Weiss did, he said, okay, I'm going to construct an almost periodic function. How am I going to do that? I'll start with 9 squares. Okay, I'm going to take one function, whatever you choose, for example, identity. So I'll place here identity, and then in the rest of the copies, what I'll do is I'll just shift the same function. So that if I'm sitting here, I'm going to see the same function. If I'm sitting here, I'm going to see the same function. And so this is going to be z, but I need to shift it by w1. This will be z, and I need to shift it by w2, etc. And now I need to have some kind of a pasting process. So I will remove these corridors here to allow for pasting. And somehow, if the corridors are narrow enough and the error is small enough, this will give you what you want. Okay, so this will be step 1. And then in step n, you're going to do the same, but these squares are now obviously bigger. So this would be, for example, 1. And so this would be, for example, 3 to the n now. So what I'll do is I'll put here fn minus 1. And here I'm going to shift by minus w1 fn minus 1. And so on. So instead of doing minus w, I shift it like so. And I shift the rest. And again, as before, I paste it here. So that was his original construction. And then when he saw this question, and actually he needed to give a talk in an analysis conference. And so he said, okay, what can I do? I can modify this to answer the first question. How am I going to do that? I'm going to keep a list of polynomials which are dense. So for example, polynomials with rational coefficients. And then instead of placing here z1, I will replace the identity with p1. And I will put here the translations of, say, p1, like I wrote it before. And what I'm going to do in step n is I will still, after pasting, I will still place fn minus 1, but I will reserve 1 square for the next polynomial. So for example, here I'm going to put pn instead of fn minus 1. And then you do the same pasting technique and everything works great. Wonderful. What about the fact that I said that in the first paper, he showed not just one, but many? So how can I approximate general, somehow have a larger variation of dynamics? So for this, oh, hold on. There's one more thing I wanted to say about this picture. So one way to extend this is basically the solenoid. Okay, so the solenoid, one of the ways to look at it is you look at the product of the one sphere with some sequence of integers. Okay, here my integers are always 3, but it doesn't have to be like that. For example, here you can see an example of the solenoid where the yellow layer is 4 by 4, but the red yellow is 3 by 3. Okay, so it has to be integers, but essentially you replicate the same trick. And what's nice about the solenoids is that for every k, you can always write your group as, so sk will be my squares over there, cross some, say, bk. Okay, so BK will be a subset of your group. SK are the squares, and you just write it like so. What does it give me? It gives me, because I can write it like this, but I can also write it as SK plus 1 cross BK plus 1. So every element from BK plus 1 has to contain these NK plus 1 squares from before. And this is what gives me this picture. Okay, so in a sense, you, in your mind, you need to keep for every element in BK, you hold in your brain one of these squares that have NK by NK copies of SK minus 1. Okay, and now if I want to extend it for general actions, what I can do is, well, they're not really solenoids, but in a sense, they're almost solenoids. In what sense? Well, my picture will not be as neat. The squares will not be well organized, but there will be some kind of a square covering. So in this case, what will happen is you will have a sequence XK of spaces. SK can be viewed, realized as a product of BK, SK cross BK. Again, BK is a subspace of your X. It's essentially a set of measure 0. But it can borrow some kind of a probability measure from your X. And your XKs don't cover the entire X. But we do know that XK grow to X. So because they grow to X, this is why you get all these spaces, unlike before. So before you didn't have spaces. You created these corridors because you needed space for pasting, but you didn't have spaces at all. And here we do have these spaces, and I don't quite know where the cubes are aligned. Okay, nevertheless, I can repeat exactly the same process, right? There's no reason for me not to reserve some specific square, place their Pn, place in the rest of them translation of the previous function, and paste with Runge. We use Runge for this. Runge is easy and nice. Okay, so this answers the first question, but now I want to pivot a little bit and talk a little bit about high dimensions. So what's the problem with high dimensions? There are many problems with high dimensions, as we know. And oops, that was not expected. Let me erase this. We don't need this anymore. And just to give a flavor of the issues, at least the ones that bug me particularly, I want to illustrate two things. So in high dimensions, some properties kind of extend naturally nicely, like maximum principle and things like that, but then other things fail miserably. One example to keep in mind is called, I hope I'm spelling his name correctly, Herglot's, I think, figure. So he basically constructed a set that looks like an L, where you give me whatever function you want here, which is holomorphic, and he can extend it to be a holomorphic function on the polydisk. And what is the problem with this? The problem with this is if you now take, let's imagine that this is a polydisk, okay? And you puncture it in the middle, I can still sneak around this shape here, right? Put it here. And any function which is holomorphic here, I can extend to the entire disk. So you don't have this phenomena that we have in one dimension. For example, in one dimension, 1 over z will be holomorphic in the disk once we remove the origin, right? Everything's fine, but it cannot be extended. Somehow now that we're going to 2 dimensions, it no longer holds this strange phenomenon. Yes? I do not know.
Yeah, it's Herglot's.
Okay, so it's misspelled. I'm not surprised. Not surprised at all. The second part, which I will not get to talk a lot about today, but still bothers me, and maybe towards the end we can, well, I think from the statement you'll already understand why, is that Jensen no longer works. So in 2 dimensions, we have this beautiful Jensen formula, right, that relates zeros of entire functions with some sort of growth rate, right, Newton-Lima stuff. But in dimension 2, so this is d equal to 1, but in dimension 2, we have an example by Kornalba and Schiffman from 1972, and they showed that you can give me whatever sequence of integers growing to infinity as fast as you would like, and they generated an entire map so from C to C, such that if you count the number of zeros of f inside a disk of radius 2 to the n, let's put it 2 to the k because I had. So this is going to be bigger than this nk that you got to choose. But on the other hand, the growth rate of f is, so f in absolute value is always less or equal than e to the log squared absolute value of c. So you will lose this connection between zeros and growth rate. Okay, and in particular, we know that we don't have Runge. Nevertheless, we do have something. So there's a theorem called Oka-Weil theorem. From digging up a little bit in the literature, I found out that it was, I believe it was independently proven by both mathematicians. There's like a 1-year gap. And I will first state it, and then I will explain the components of the theorem. So in a sense, it's a high dimensional Runge, and it has 2 years. One belongs to one author and the other belongs to the other author. And it states that if K, now we're in CD, is a compact polynomially convex, which I will explain in a minute what it is. Set, then indeed you can Runge it. So then for every f, which is holomorphic in some neighborhood of U, there exists E such that the difference between them is bounded. And of course, I'm missing for every epsilon here. Okay, so a detour for polynomially convex sets. So I will write the formal definition, but I also want to hand wave kind of what it means, okay? So you start by defining what is the polynomial convex Hal. Of a set. So the polynomial convex Hal, that's going to be all the points Z. Intentionally, I'm not writing where it sits. It will be C or CD, depending on the context, such that for every polynomial, if you try to look at the absolute value of P of Z, and you compare it with the supremum of the polynomial in your K, then this will be less than this. And this will be denoted k hat. So in particular, you can see that k is a subset of k hat always, right, by definition. But evidently, so some examples. So in dimension 1, every simply connected set is polynomially convex. Oh, sorry, I defined the hull. I didn't define what it means to be polynomially convex set. So K is polynomially convex if K hat and K are the same. So in a sense, the polynomial convex hull of a set is all the set of points such that you cannot distinguish between the set and the point by using polynomials, right? And a set is polynomially convex if you cannot, for every point outside the set, you can always distinguish between your set and that point by some kind of polynomial. So the fact that in dimension 1, every simply connected set is polynomially convex kind of sits well with the fact that we have Runge, right? Another example, which is easy to kind of understand in your brain, is convex sets are polynomially convex. Okay, and also if you look at product set in the product space. So products of polyconvex sets are polyconvex in the product space. Okay, so we have a very large class of things to work with. Great. Now we want to use this theorem, but we need to first somehow show that the sets where we want to do approximations are polynomially convex in some sense, right? So we're going to start with this simple example, and the way to do it is a brilliant observation by Eva Kalin from 1964. So in the end, I'm still I'm still fighting with myself whether we're using her result or just her ideas, because it is so simple and elegant that you don't have to use the theorem as a black box. You can just use the idea. So Eva Kalin in 1964 had the following characterization for polynomially convex sets. So let's assume that I have K1 and K2, and they're convex sets in CD, and assume that there exists some polynomial such that if you look at P of K1, P of K2, you take the polynomial convex hull and you intersect it, then this is an empty set. So we have some kind of a polynomial which distinguishes between these two sets. Then in this case, we can switch between the union and the convex hull. And essentially, the idea of the proof is so simple, because what she's saying is, okay, we already have this polynomial. It distinguishes between the sets. And what it does is it takes the problem in CD and reduces it to a problem in dimension 1. And now I can use Runge, right? So you take your new sets, you call them, say, K1 tilde is going to be P of K1, and K2 tilde is going to be P of K2. These are two sets in C. They're separated because of this, and so I can apply Runge So I plot Runge, I get a polynomial with Runge. Let's call it Q. And now the new polynomial I will work with is Q composed with P. And this polynomial, it's a polynomial composition of polynomials, and it will distinguish between the two sets, and I'm done. So we kind of copied her idea. I'm going to call it the main lemma, even though we don't call it the main lemma, but. And we use it for, I want to say, kind of a specific case. Let's assume that I have two compact sets, and there exists a hyperplane separating them. Then you can say the same. So actually, I assumed that they are polynomially convex, but it doesn't change. The statement is the same. And we use a similar idea. So what we do is you can assume this, because if you think about the definition a little bit, being polynomially convex is translation and rotation invariant. And so because polynomials are, right, if you rotate or translate a polynomial, it would still be a polynomial. And so you can assume that this hyperplane is just, say, the real line being equal to 0. You project your set on the first coordinate, z1. It's on one side, half of it is on one side of the set, the other half is on the other side of the set, right, of the real line. You have this picture. So I'm not going to draw the high dimensional thing, but you have this picture. And my hyperplane created a situation where one set is here and the other set is here. I'm using Runge, I'm done. Okay, so conceptually, it's a very simple lemma. Okay, so now that we have the main lemma and we have the Oco-Weil theorem, it is, I believe, quite intuitive or even trivial to understand what to do here, right? Because each one of these cubes, each one of them is polynomially convex, because of the example, the second example that I wrote, or the third one, either these cubes are convex sets, but they're also products of lower dimension polynomially convex sets. So each one of those is polynomially convex. They are separated by these hyperplanes. And so the union is polynomially convex, and we're done. Great. The difficulty was, what do we do with this very different picture where we can use an almost solenoid, which is not a solenoid? So here we have a problem because, well, if I want to pass these hyperplanes to use the lemma, I'm going to get stuck. So for example, the hyperplane that is connected here, it's going to get stuck here, right? So I have no way of proving that this is polynomially convex. So what we did instead, and this is an idea that kind of steals or is inspired by my second work when I tried to take this picture and have good growth bounds on this. So what we do here instead is, instead of looking at polynomially convex sets, we define something which is called an almost polynomially convex set. So what is an almost polynomially convex set? Let's assume I have a set U in C, or let me call it K. K in CD. If for every epsilon, I can find a subset of K, which satisfies two things. So first of all, it is polynomially convex. And the second condition is that the Lebesgue measure of the difference between the two is less than epsilon, then K is almost polynomially convex. Okay, now here, what I did, here also kind of used these approximations, because remember that I told you originally, if you want to create the full group, for the full group, you need the full square full copy of each square, but I couldn't paste if I had the full square. I had to remove these boundaries. So once you observe that we don't really care if we remove the boundary or somewhere else in the cube, we're allowed to remove small strips. So there's no obstruction in, for example, taking this hyperplane. And yes, I'm removing something very thin from this set, but it's okay. I don't mind, right? In terms of measure, it's not going to change anything, right? However, there is still a problem. What is the problem? I have many squares. And when you remove a lot of thin strips from many squares, even if they're very thin, you're going to lose too much measure. That's one problem. Problem two is that we need some kind of local uniform convergence to get the density property, because I want to hit the jackpot. I want to do 1 and 2. So if I want to have a dense orbit, but for example, I keep removing from this cube all these lines, right? Very, very fine lines, I will end up not having a dense orbit. So for this, we use the method, I like to call it divide and conquer. So we do it in 2 steps. The first step is we pick a grid, and the important bit is that the cubes of the grid are the same size of the cubes here. So I can rescale everything to have size 1.
Sorry, I got a little bit lost here. So for the almost polynomial convex sets, does the version of alpha wild still work?
No, but I will apply it to these k epsilons. So I will work with the k epsilons, and the idea is just like here, I remove the boundaries and I don't care, flattened boundaries. I'm going to remove here some strips in the middle and it's okay. Right, so the first trick is divide and conquer. Instead of trying to work with all the cubes together, where from each cube you might remove so many strips because it somehow intersects with a lot of those lines, I will start by creating a grid, and the grid has to have the same cube size as my cubes. So my drawing is approximate, but bear with me, okay? Has to have the same size, but as I said, you can just rescale everything to be 1, and that's okay. And now, what do we know from the lemma? We know from the lemma that if I manage to show that the intersection inside each one of those is good, then we're good, right? Because it's a grid. Because it's a grid, they're separated by hyperplanes. And so if inside each one of those everything is okay, then the union is okay. All right, so the first step is we remove these grids. Very, very thin. Kind of clear? Okay, so I somehow reduced my problem from dealing with many sets very, very far away, somehow maybe affecting one another. You see that this cube somehow affects this cube, into just dealing with 1 square every time, 1 grid cube. Now inside this grid cube, the first, I want to say obvious or simple thing to do is, okay, I have these, if you think about it a little bit, you see that every edge corresponds to an intersection with a cube. So the number of them is bounded by 2 to the d. I will just remove all the flattened hyperstrips inside. So I will remove this hyperstrip coming from here, and a hyperstrip coming from here, and one coming from here, and so on. But only inside the grid cube, not outside. I don't need to do it outside the grid cube, right? Because we're doing divide and conquer. Okay, great. Let me color the cubes, otherwise it won't be clear what's the cube and what is outside now. So this was 1 cube. This was a cube, right, that I removed a strip from. This was a cube that I lost a strip. Okay, great. But I still have that second problem that I mentioned. So now I'm only removing something like 2 to the 2D strips. So the number of strips is small, and I can make them narrow enough to have this almost polynomially convex property. Okay, but the second problem I described was that if every time I remove from my cube, say a middle centered strip, then I have a problem, right? Because I keep shredding it to smaller and smaller pieces, I will not have the property that the orbit is dense. So what do we do in this case? Well, we define a priority. If you look at the intersection of two cubes, say yellow is my grid cube, and let me draw 4 of those. And I know I'm drawing everything in dimension 2, but it works in higher dimensions. And let me put a collection cube. So this will be some kind of a collection cube. Okay, because of they are of the same size, the center of the collection cube, the red cube, is going to sit in one of those 4. And because they are of the same size, because they have the same edge length, the cube, the grid cube that contains mine center, the collection cube will contain the center of the grid cube. You have this duality. And so it's unique. I'm going to give priority to this special cube, the cube that contains my center. Okay, so for example, in this picture, this is my special cube. I will give this priority. What does it mean to give it priority? It means I'm first decomposing the cube by the hyperplanes that are composing this special cube. And now this I'm going to leave as is. This is no touch. No touch zone. Now each one of those is, well, it's no longer a cube, but it's a box. Still has a finite number of guys. And now within each one of those, I'm going to do the same process I did here. So I will remove all of them. So this is actually not a good example because they don't let me change it a bit to be like this so that we'll have some kind of interaction between the guys. Okay, so here I will remove this from this box, this strip and this strip. So now this is polynomially convex, this is polynomially convex. Here I'm going to remove all the strips limited to this specific box. Right, and here I will remove this. So now each component is polynomially convex. They are separated by hyperplanes. You do it carefully. You say, okay, this set is polynomially convex because everything inside is union of polynomially convex separated by hyperplanes. This satisfies the same. This satisfies the same. Okay, now how do I paste this? This and this are separated by a hyperplane. So the union is this and this are separated by a hyperplane. So by this hyperplane. So the union is, and then this and this. So you have to do it very carefully in terms of like how you paste things. This is the last thing that you add, but it works. And you have everything you wanted. So we don't have the approximation so nicely like in the two-dimensional example where you have here the full cube. I had to remove some things, but for each one of them, at least a quarter will stay true to its original structure. Okay, great. So we've answered these questions. Actually did not write one theorem on the board, but I guess you know what they mean. What is lift? So people who followed what I've been doing for 2 seconds or more probably can expect the next question, the next part of the talk, which I won't say a lot about it. So the next natural question is growth. When I asked Benji about growth, he told me, you're on your own. What can we say? So if we go back to my result from 2022, we do have a lower bound. So the functions in the support are going to grow like e to the log. And here we're going to have d over d minus 1 of r. This is not hard to see. It is also not too hard. So it's not something that I've done, but it's not hard to construct an upper bound of exponent of d exponent of log squared. You just look at a product of entire functions from dimension 1. You can see that there's a gap. These guys agree only for d equals to 2. For higher dimension, it's not clear what to do. There are 2 works that I'd like to somehow put in asterisks here. So there's a work by Buchowski, two Polteroviches, Igor Shluchin, I guess he spells his name like this, and then Wojtek, whose last name I cannot pronounce or write. They have a result where they discussed growth rates of, so they didn't discuss, okay, they were talking about something that is somehow very reminiscent, but not exactly the same. So their project was, you look at a function, holomorphic function, and you look at the connected components of where this function is less than some epsilon. Okay, and you count how many of them have a zero inside, have an honest to goodness zero. And they related the number of connected components with some kind of a growth rate. In a sense, morally, they did the reverse. They chose a growth rate and they bounded the number of connected component that you can have. It's completely different from those things. First of all, we do not require it to have a zero, but also the powers are significantly different. So I believe their powers are something like this. And maybe I'm missing another exponent. But this is a work which is interesting, and maybe if things don't match up between this and this, then maybe this is a place to go look for answers. Something else that Kirill told me about yesterday is that there's a work by a French mathematician whose last name is Novich, and she did something of Runge like pasting something like this. I haven't looked into it deeply enough, but it looks promising. So maybe from her work and what he's been talking about yesterday with the lemon skates, I can say something about upper bounds. And I guess I'll stop here. Thank you very much for your attention.